let's talk about similar triangles. So what makes a triangle similar? So say we have triangle 3, 4, 5, and we have another triangle 6, 8, 10. And tell me what you notice about these two triangles. Well, first off, in similar triangles, you can see that all corresponding angles are congruent. Okay, so all corresponding angles are congruent. Okay. Second thing you might notice is that all corresponding sides are in proportion. Now, what does this mean? In proportion, well, let me give you an example. So if we take, let's say, the biggest side, okay, and we divide it by the biggest side of this triangle. Well, guess what? This is going to equal to the smallest side divided by the smallest side of this triangle. And this is going to equal to the medium side divided by the medium side of this triangle. So you see all of these sides, this is what it means to be in proportion, okay? So if you take any one of the sides, divide it by its corresponding side, it's going to be equal to any other one of the sides divided by the other side, okay? So these are just properties of some similar triangles. And we're going to learn about some theorems that we can use to prove that two triangles are similar. So let's get into it. First postulate so this is called the AA similarity postulate. Okay, and what this postulate basically tells you is that it doesn't matter what the sides, so we're not given any sides, okay, right now. There are no sides. But if we're given two angles of a triangle are congruent to two angles of another triangle, then those triangles are similar. So if this is triangle ABC, this is triangle DEF, you would say that triangle ABC is similar. So you can think of this as the congruent symbol without the two equal signs, kind of. Triangle ABC is similar to triangle DEF. And this is by the AA similarity, okay? AA similarity postulate. So, let's say if I will just give you a random example. Like, if this angle and this angle are congruent, well, these two triangles, this triangle and this small triangle, would be similar. Why? Because vertical angles are congruent, and guess what? You have two angles that are congruent, which means that this triangle is similar. Another postulate, this one's called the SAS similarity postulate. Okay? SAS similarity postulate. And let me show you an example of this. Let me go here, 3. Let's say this is 3, this is 4, 6. Or let's say this is 9, this is 12. If you have two sides, right? You have two sides, right? And you have this angle right here. If the two sides are in proportion, meaning that, let's say, if we divide 12 over 3, so this big side over the small side, and you divide the small side over the, oh, my bad, okay. Next postulate I'm going to be talking to you about is the SAS similarity postulate. This basically states that if you have one side, let's say we're given two sides and one angle, okay? So if the sides are in proportion, meaning if I divide the small side by small side, big side by big side, so this is kind of like the scale factor. So if kind of the scale factors, you can think about it, of the triangles are equal. So, and the angle in between, we call this the included angle, kind of the angle that's formed by these two sides. If the included angle of these triangles are also congruent, well, these triangles are similar, okay? So, if two sides are in proportion, and included angle is congruent, those two triangles are similar. Okay? So if two sides are in proportion and the included angle is congruent, then those triangles are similar. Okay? So an example of the SAS similarity postulate is if we had a triangle that looked like this. Okay, so this is 5, 10, this is 4, this is 12. This is 5, this is 10, this is 4, this is this is 8. Okay, so what I like to do, let's call this triangle ABC and the big triangle ADE. Now, in order for you maybe to visualize better, now what I like to do sometimes, especially if you're new to this, is I like to separate the triangles. Okay, so this is the small triangle and this is the big triangle. Obviously not drawn to scale, but so in the small triangle we know that it has sides 5 and 4. In the big triangle we know that it has 5 plus 10, that's 15, right? Because this includes this whole side, and this AE includes 4 and 8, 12. These triangles, they share a common angle. You see, angle A is in both of these triangles, which means this angle has to be congruent to itself. And then you can use SAS similarity theorem. Use SAS similarity theorem because guess what? These sides are in proportion. 15 divided by 5, so big side divided by big side is equal to small side of the big triangle divided by small side of the big triangle. See, these both equal to 3, which means that these two triangles are similar, okay? So if two sides are in proportion with two other sides and the included angle is congruent, well, you have yourselves two similar triangles. Finally, we have the did SAS last time, but SSS similarity theorem. So, let's say we have 5, 10, 15, and say that we have 20, 60, 20, 60, and 40. If three sides of one triangle are in proportion to three sides of another triangle, those triangles are similar. So big side divided by this big side is equal to medium side divided by medium side. I'm just saying, if this was true, and in this case this is true, well, you have yourselves similar triangles. So 60 divided by 5, that's going to be 4. So all of this equals to 4, right? But don't always think that two triangles can always be similar. Yeah. So if you see something like this, like, you shouldn't automatically assume that it's similar. Obviously, you have to try to test out all of this to make sure that everything's all right. And in case you're wondering, are congruent triangles similar? So are congruent triangles similar? So this is the congruent symbol, this is the triangle symbol, and this is the similar symbol. And the answer to that is, well, yes. First of all angles are congruent, so you already got that going. in addition, all sides are congruent, so basically every theorem works for similar triangles. Yes, of course. Congruent triangles are going to be similar. So, given that AB is parallel to D, how can you prove that triangle ABC is similar to triangle EDC? First thing you always want to do when you're writing a two-column proof is you want to write out your given statement. And you're given that AB is parallel to D. Now what? What do we know about parallel lines and transversals? So imagine this, okay? This is the... Let me just do this in a different color. So imagine this, right? I'm just outlining it so it's clearer to see. You have two lines and then you have this transversal. When this occurs, we know that alternate interior angles are congruent, which means that this angle and this angle are congruent, okay? So we can say the same thing about this part. This angle and this angle are congruent. So angle A is congruent to angle E. And what else? Well, guess what? There's another side. We can make another transversal right here, right? So right here, A to B, and then this is another transversal, okay? BD is now our transversal this time. So imagine like this, okay? So this is kind of like the shape, like the Z we made with our kind of diagram. And in this case, alternate interior angles, this alternate interior angle, and this alternate interior angle, right? So you can see how this part and this part are congruent, just like how this part and this part are congruent. So based on this, you can also say that angle B is congruent to angle D. And the reason for this is because when a transversal cuts two parallel lines, I'm just going to use the parallel symbol. This is the parallel symbol. When a transversal cuts two parallel lines, alternate interior angles are congruent. Okay? Alt in angles, that's how I abbreviate it because I'm lazy. When a transversal cuts two parallel lines, alternate interior angles are congruent. Okay? So this angle, congruent. This angle are congruent. Okay? Final step. What do we have? We have two angles. And guess what? We can say that triangle ABC is similar to triangle EDC. And this is because of the AA similarity postulate, okay? So we use this transversal to get two congruent angles, and we just use the AA postulate to state that these two things are similar. And in case you're wondering, you can also do vertical angles like this, okay? Vertical angles are congruent, but that would be an extra step, so no need for that. Given that BC is parallel to D, prove that AB, so this part divided by this whole part is equal to this part divided by this part. Now, obviously, you already know what to do at this point. Write out your given, okay? Now, let's start to plan this out, okay? So, what we want to do is we want to prove this triangle. So if I just separate these two triangles, I want to prove that triangle ABC is similar to triangle ADE. Why? Because we know that in similar triangles are, their sides are in proportion. meaning that this big side, or in this case, this small side divided by this big side, is equal to this small side divided by this big side, right? So because their sides are in proportion, we got to prove that they're similar first. So let's do it. Once again, we're dealing with some transversal stuff and parallel line. So what I'm going to do, once again, is I'm just going to highlight this part, okay? Just going to highlight this part. Now, imagine a transversal like this. You have two lines, okay? And this is the angle that's formed. So we're starting at this angle. Well, in this case, we know that when a transversal cuts two parallel lines, corresponding angles would be congruent, meaning that the angle below this, you can think about it, this angle below this would be congruent. So you would say that angle ABC, or whatever, I'm just going to write angle B, is congruent to angle D. And what else? Once again, we can draw another line here to here, right? Imagine we have a transversal like this. This is angle C. Well, guess what? This corresponding angle, this kind of, you can think about it as the angle below, is going to be congruent. So we're going to say that angle C, this angle is congruent to this angle. Angle C is congruent to angle E. And this is because, well, I already said it, but when two parallel lines get cut by a transversal, corresponding angles are congruent, okay? So whenever you're writing a proof, you don't have to, you can kind of like paraphrase the idea. You know, you don't have to say like the exact meaning that like the teachers give you. As long as you say like the general idea, you're good, okay? So when two parallel lines get cut by a transversal, corresponding angles are congruent. So we have this angle is congruent to this angle, and this angle is congruent to this angle. Well, guess what? This triangle got two angles. This triangle got two angles. Triangle ABC is similar to triangle ADE. And this is because, guess what? A similarity. And now, last step. We can say that AB over AD is equal to AC over AE. Why can we say this? Well, because we know that, once again, in similar triangles, their sides are in proportion. So this small side right now is going to be proportional to this big side, right? Because you can think about it, right? You can think about it. If I separate these two triangles, okay? So these two angles are here, and then this big triangle, these two angles are here. So this side, starting from here to here, that's going to be in proportion from this triangle from here to here. So aka AB divided by AD. And that's going to equal to this whole side, right? This AC side divided by this whole side because it's in proportion. So this is going to be corresponding sides of similar triangles are in proportion. So corresponding sides of similar triangles are in proportion, meaning that small side over big side equal to small side over big side, assuming that, you know, they're corresponding parts, obviously. Now, another thing I want to show you. Now, this is pretty cool, okay? So, I want to draw a right triangle, okay? So, I'm just going to draw a right triangle. And what I'm going to do is I'm going to make an altitude. What is an altitude? Well, an altitude in a triangle is kind of a line goes from the opposite side goes to the opposite side like this to make right angles. So it's perpendicular, you can kind of think about it, to the base. So I'm gonna draw a line here, and it's gonna form right angles. Now, what's gonna happen is that if I separate these triangles, so there's actually 3 triangles here. This triangle, and this big triangle, okay? So, this triangle, and the big triangle. And what happens, well, I already have the big triangle drawn, but I'll draw again. What happens is that these triangles are similar, which is actually kind of crazy. So, assume that, this angle is 40. That means this angle right here, because it's a triangle, this angle has to be 50, right? Because a triangle has 180 degrees. But if this side is 50, and this is a right angle, well then, this side has to be 40, because 50 plus 40 gives us this 90-degree angle. And that means that because this is in this triangle, this side is 50. Well, if this side is 50, well, guess what? This side has to be 40. And you can see that, voila. All the angles of the triangles are congruent. Well, we could have done it with 2 angles, but I just wanted to show you that these triangles, all of these triangles are similar. And this is going to connect to something, after I talk about geometric means. But this is actually a pretty crazy theorem, and it's actually really useful. So let me show you something. So what is the geometric mean, okay? A geometric mean, you might have heard of the arithmetic mean. Like if you want to take 3 and 2 and find the arithmetic mean, this is just the average, okay? So you just add these 2 up and divide it by how many terms there are, which is in this case 2. Geometric mean is different. The geometric mean, I'm just gonna write G, is equal to the square root of kind of the stuff. So, the stuff in this case, let's say if this was 3 and 4, the geometric mean would be the square root of 3 times 4, which would be 2 radical 3, okay? Another example, the geometric mean of, let's say, 4 and 9. Geometric mean is going to equal to square root of 4 times 9. And in this case, this is just going to equal to 6. So this is just the geometric mean, okay? This is the geometric mean. Now what happens is, when we create this right triangle, let me just do a quick sketch of it, okay? This side, okay, so the altitude side is going to be the geometric mean of these 2 kind of mini sides. For example, if this side was 4 and this side was 9, the geometric mean of 4 and 9, well, we already did the problem, but geometric mean of 4 and 9 is 6. And the altitude is going to be 6. The altitude is the geometric mean of the smaller sides, okay? So that is one important thing. Another important thing. The geometric mean of this whole side and its adjacent side is going to be equal to this side. So if we were trying to find the length of this side, obviously we can use the Pythagorean theorem, a squared plus b squared equals c squared. But in this case, we're going to use the geometric mean. This side, let's call it y. Y is going to be equal to the square root of, in this case, this is going to be the whole side, okay? So whole side, 4 plus 9 is 13, times the adjacent side. This side and this side. This is the adjacent side. That's going to equal to 2 radical 13. So this is, y is going to be equal to 2 radical 13. The length of this side is going to be, well, this is going to be really similar. Let's call it x. X is going to be equal to, remember, the geometric mean of this whole side times the adjacent side. In this case, the adjacent side is 9. And what you're going to get is 3 radical 13, okay? So what we kind of learned from now is that if we have a triangle like this, and let's call the sides A, B, C, and let's call this side D. The length of AB equals to the geometric mean of AC times AD. Okay, so geometric mean of this whole side times the adjacent side, The geometric mean of BC, the length of BC is going to be the geometric mean of AC times DC. So the geometric mean of this side is going to be this whole side times the adjacent side. And the adjacent side, well, this is going to be this portion, okay? So kind of the portion that belongs to this triangle. So this wouldn't be the adjacent side because it's not on this triangle. So it's the part on the triangle. And BD, the altitude part, is going to equal the geometric mean of AD and DC. So AD times DC. Okay, so when it's the geometric mean of the altitude, it's not the whole thing. It's part times part, okay? That's how I like to think about it. What I want you to do right now is I want you to find the measures of X, Y, and Z, okay? Using the formulas that were provided before. And you can pause the video, scroll back a little bit, and, review the formulas a little bit. And I'm assuming that you've paused the video, and let me show you the solution. X looks like the easiest to go. The geometric mean, or the length of X, is going to be equal to the square root of part and part, okay? Part by part, okay? And this is going to equal to 3 radical 6. Okay, so we found X. X is equal to 3 radical 6, okay? 3 radical 6. Now, we know that the geometric mean of Y is equal to this whole thing, okay? So, this is going to be the whole thing. So, 6 plus 9, that's 15, times the adjacent side, aka the part, you can think about it as the part that's on the triangle. The 6 is the part that's on this triangle, which means that this is going to be multiplied by 6. And this is going to give you, you can rewrite this as, well, we know 6 times it's going to be 80, or actually no, let's simplify this first. So 15 can be broken up to 5 times radical 5 times radical 3. 6 can be broken up to times radical 3 times radical 2. This will make a 3, so this is just going to be 3 radical 10. Okay, so Y is equal to 3 radical 10. Here. Z is going to be equal to the geometric mean of the whole thing. So 6 plus 9 is the length of this whole thing. And this is going to be multiplied by the adjacent side, the part that's on the triangle. That's 9. And this is going to be equal to 3 radical 15. Okay? So you see how useful this thing is. You don't even got to use the Pythagorean theorem. In this case, I don't know. This feels faster than using the Pythagorean theorem. You don't need to use a calculator for this. This is a pretty simple calculation. So, you could use the Pythagorean theorem, and you're going to end up with the same results anyways. So, this is just like a quicker route. Now, let's do something like this, okay? A little bit of a challenge, maybe. So, let's say this is 15 now. This is 6, and this is X. Okay, this is a little bit of a challenge. And Y and Z. Let's see if you can solve this. We know that the geometric mean of part and part, so this is going to be 6x, is equal to the altitude length. Okay, So altitude length is equal to geometric mean of part and part. Now, in order to solve for x, we got to square both sides. And we're going to get 15 squared, I think that's 225 equals 6x. And x is going to be equal to 225 over 6. I don't know what that is, but I'll just get my calculator real quick. So 225 over 6, 37.5, okay? 37.5. And this will go right here. What is y? What is y going to be equal to? Hold on, let me just erase this all real quick. Okay, so what is y going to be equal to? Remember, y is going to be equal to the geometric mean of this whole thing, okay? So 43.5. So because it's 37 plus 6, and this won't be multiplied by, well, you guessed it, this is kind of the adjacent part, times 37.5. And putting this into my calculator, I get times 37.5. That's going to give us our, I'm just going to round this. This isn't exact, but this is about 40. Okay, I'm just saying about 40. So this is going to go here, 40. Finally, let's solve for z. Z is going to be equal to the geometric mean of this whole side. So this is going to be 43. It's going to be equal to 43.5 times this adjacent side. Okay, so geometric mean of whole side times adjacent side. And this is going to be equal to 43.5 times 6. It's going to be equal to, I don't know, once again I'm rounding. This isn't an exact value, but this is going to be about 16. So you can see, once again, just being given two sides of this one long side of a triangle, you can find out these three values, which is pretty cool in my opinion.